All right, so this is going to be our last lecture from Chapter 5. You are going to have an additional day of homework, and because I want you to keep practicing with different types of proofs. So we're going to talk about one other topic that is not specific to contrapositive, but some of these are going to be easier to prove with contrapositive, and some of them are going to be easier to prove with direct. And both your work today and tomorrow, you will have the option to pick which strategy you think is best for that problem. So remember, just look at like which is more complex, the hypothesis or the conclusion. Today we're going to talk about modular algebra, and so we're going to define that over here. Now, in terms of notation, what you'll see what's like an equal sign, an equivalent sign of two numbers or two variables in terms, and then it's written mod n. And what this means is that A is equivalent to R in mod n, that's how we'd read that, where A is equal to some quotient n plus R. So the way that I think about this is that if you think about this in terms of division, Q would be the quotient and R is the remainder, meaning that if we had the division problem, A over n, that would equal the quotient plus the remainder over n if we think about it in terms of a long division problem. One important thing to note is that if we say that n divides A, that implies both directions that A is equivalent to 0 in mod n, since 0 would be the remainder there. So another really important way that will be helpful in your proofs is this, and we're going to prove why it's true, and then you'll be able to use it in a lot of your proofs, and I'll show you what I mean there. So here it says let A and B be integers and n is a natural number. If A is equivalent to B in mod n, then n divides A minus B. So we're always just, in this place I'm going to use direct proof. I'm going to start with the hypothesis. So A is equivalent to B, and I will use the definitions there, since what that means is that they have the same remainder. So I'm going to rewrite it slightly differently than I have over here, because if they're equivalent, that means that they're also equivalent to the same R. And so I will say, well, A is equal to quotient 1n plus R, and B is equal to some other number, maybe the same, maybe A and B are the same, it doesn't necessarily mean that, but they have the same remainder, and where Q1 and Q2 are in the integers. Now what I'll do from there is we're worried about A minus B, so I will consider A minus B, and with substitution we then get Q1n plus R minus, remember we're subtracting the whole thing, Q2n plus R, which would simplify it to Q1n minus Q2n, which says that n is equal n times Q1 minus Q2, since the remainders cancel out with the subtraction. So now we have A minus B is equal to a product of n, and what we will do here, and this is something I've mentioned on some of your homework and quizzes as feedback, is I will make sure that I'm going to say, well, Q1 minus Q2 is equal to, just, I'm just going to use K, in the integers because of closure, because integers are closed under subtraction. You need to argue that this is true. This is a really important part. If that's not true, then you will not have a complete proof. So then A minus B is equal to NK, which means that n divides A minus B, which is what we wanted to show. Now, again, this is going to be a really helpful way to prove a lot of the problem sets in the homework, and I'll show you an example. So here, if we have a and b are in the integers, then a plus b cubed is equivalent to a cubed plus b cubed in mod 3. So using the first one, we can just show that 3 divides the difference. A plus b cubed minus a cubed plus b cubed. So this is just using this idea here, that a and b are equivalent in mod n when n divides their difference. So we want to show that 3, since that's our mod, divides the difference between the two equivalent parts. And so that just makes this rule that we proved in number 1 just makes everything a lot easier from there. Now, we're going to start by just considering a plus b cubed minus a cubed plus b cubed. Remember your binomial theorem, that's equal to a cubed plus 3a squared b plus 3ab squared plus b cubed minus a cubed minus b cubed. We can simplify that to 3a squared b plus 3ab squared, which is 3a squared b plus ab squared. I'm going to say that a squared b plus ab squared is equal to c, which is an integer, since a and b are integers, by closure under multiplication, which covers the exponents as well, and addition. Therefore, by the transitive property, we can say that a cubed here, a plus b cubed minus a cubed plus b cubed is equal to 3c. So 3 divides the difference, which remember that's what we wanted to show, which implies that a plus b cubed is equivalent to a cubed plus b cubed in mod 3. There you go. So hopefully that will help. Thinking about modular algebra, it seems like an odd thing. We actually use it all the time, so if you get stuck, think about modular algebra as the way that we tell time, right? We go around and we're just counting by remainders. So every time we divide by 12, we just figure out exactly where we're back to on the clock in terms of an example. If you have questions on this or any others, you only have one video, as I said, this week, and then you will have 2 separate problem sets from the homework. Please make a meeting if you're stuck on anything, or if you just want to talk through the presentation problems, any corrections from previous quizzes, or any other problems in the homework. Talk to you later.